Hello, in this video we're going to look at an introduction to polynomial functions. So far this semester we've looked at what is a function, how to transform functions, we've looked at linear functions, we've looked at quadratic functions, and now we're going to look at polynomial functions. So let's get started. We might want to start with discussing what is a polynomial function. So we've seen some polynomial functions in the functions we've already been looking at. A polynomial function, it could be a quadratic, a cubic, a quartic, and so on. Essentially, it is a function that is written in the form f of x is equal to a sub n x to the n plus a sub n minus 1 times x to the n minus 1, etc., plus all the way until we get a constant value, should be a sub 1. And what has to be true about polynomial functions is that every term must have a positive integer power exponent. And so the coefficients can be any real numbers, but the powers must be positive integers. So an example of a polynomial function might be f of x equals 3x squared plus 2x plus 1. All the powers are positive. You can think of the constant as being x to the 0. Okay, so I have an x squared, an x to the first power, and x to the 0. Now remember, this 1 is often assumed, and this x to the 0 is the same thing as 1. So all of our powers are positive integers, or 0 if it's a constant value. We could also have g of x equals 10x to the 7th plus 3x squared plus 2. This is also an example of a polynomial function because our powers on our x terms are all positive integers and our coefficients are real numbers. We could also have, let's make up another one. We could have something like h of x equals negative square root of 2x to the 4th plus 3x squared plus 1/2. This is also a polynomial function. The coefficients are real numbers. The powers on the x terms are positive integers. So these examples all satisfy the definition of what is a polynomial function. Based on that information, we're going to go through the following functions and determine if they are polynomial functions or not. This is a yes or no answer. This is just being able to determine, is this written in that form we saw before? I've rewritten the general form above in gray so you can see that. Now remember that we need real number coefficients and non-negative integers. So looking at the first one, we have f of x equals negative 3x to the 5th plus 2x to the 2nd minus 2x minus 10. We look at the powers of the exponents on the x values. Those are all positive integers or non-negative integers. Because it could be 0, like x to the 0. That's okay. So it's not all non-negative integers. And all of the coefficients are real numbers. And so yes, this is a function that is a polynomial function. Looking at B, we have f of x equals 5x to the 15th power plus 7x to the 5th power plus x to the 4th power. We're dealing with non-negative powers and real number coefficients. So yes, that is a polynomial function. For C, we have f of x equals 8 times the square root of x plus x to the 3/5 minus 5. Well, square root of x is the same thing as x to the 1/2. And we also have this x to the 3/5. Fractions are not integers, and so therefore this is not a polynomial function. So C is not an example because we have powers that are fractions which are not integers, so it does not work. D, we have f of x equals x squared times x plus 2. We could multiply this out, which would give us x to the 3rd power plus 2x squared. which is a polynomial because it has non-negative powers and real number coefficients. So D, example D, is a yes. And then the last one, E, we have f of x equals 1 over x minus x to the negative 5 power. Well, 1 over x is the same thing as x to the negative 1 power, which is not a non-negative power. We also have a negative power there, and so therefore this is not a polynomial function. So no. When we're looking at polynomial functions, we want to make sure we can determine what the degree of the polynomial is. The degree is the highest power of x when there are no parentheses. So if there are parentheses, you must multiply it out to find that degree, okay? So the degree, we're going to go back and look at the degrees for each of those polynomials that we found, for example, A, B, and D in the first problem. But we're also going to figure out what's our leading coefficient. The leading coefficient, which we'll abbreviate with LC, is the number in front of the highest power of x. It's the coefficient. That's the proper term. The coefficient of the number, or of the highest power of x. So on each of the examples that we saw in part 1, we're going to go back and we're going to determine what's the degree and what's the leading coefficient. Okay, so for the first one, our degree, the highest power that we have here is a 5. So our degree, this is a 5th degree polynomial. The leading coefficient is the coefficient on that highest powered term. So our leading coefficient is -3. On the second one, our degree, our highest power is 15. So it's a 15th degree polynomial. And our leading coefficient is a 5, the coefficient for that highest powered term. On this one, our degree is a 3, the highest power after we've cleared out the parentheses is a 3, so our degree is 3, and the leading coefficient is a 1. Remember that if there's not a coefficient listed there, it's assumed to be a 1. If you had something like f of x equals negative x to the third, the leading coefficient on this polynomial would be a -1. So just keep that in mind. The degree on that polynomial is 3. Okay, so just keep in mind what our coefficients are and what we assume them to be if there's not an actual written coefficient there. Next, we're going to discuss the end behavior of a polynomial function. End behavior is all about what happens on the far left and far right ends of the graph. Okay, so what happens as x approaches negative infinity and as your x's approach positive infinity. And it's determined by examining the degree and the leading coefficient. So degree, we're going to look at whether the degree is either even or odd. Okay, for the leading coefficient, we're going to look at, is the leading coefficient greater than 0, which would be positive? Okay, or is the leading coefficient less than 0, making it negative? The leading coefficient can't be 0 because then there wouldn't be a term, that term in the polynomial. So we're looking for positive leading coefficients or negative leading coefficients. We're looking at whether the degree is even or the degree is odd. Okay, so even degreed polynomials look like parabolas as you get increasing powers of 2, so 2, 4, 6, 8, they get these kind of little wavy parts to them, but they generally have the same kind of shape as a parabola, like this. If it has a positive coefficient, it's going to face upwards, just like we saw on our quadratics. I'm going to draw a little wavy part right here because depending on the degree, there might be some waves at the bottom of your parabola-esque shape. We would describe this as rising on the left and rising on the right. So if the degree is even and the leading coefficient is positive, it rises on the left and rises on the right. So we can say it rises on both sides. And they're all going to typically have that shape if it's a even degreed polynomial with a positive leading coefficient. Okay, if we have an even degree polynomial with a negative coefficient, just like when we saw negative quadratics, it's going to face downwards like this. And again, we're going to draw a little, we don't know what this looks like in the in-between, but there could be these bumpy curves, so I draw them as a dotted line. We would describe this as falling on the left. It falls on the left and falls on the right. So you could say it falls on both sides. Notice that for an even degreed polynomial, both sides have the same end behavior. Okay, so on even degreed polynomials, both sides have the same end behavior, meaning that if it's positive, they're both going to rise on both sides. If it's negative leading coefficient, if they have a negative leading coefficient, they're going to fall on both sides. That's different from what happens with our odds. Okay, with our odds, again, we're going to have kind of a similar shape, like a cubic function. We saw that when we looked at parent functions at the beginning of the semester. If we have an odd degreed polynomial, it's going to look like a cubic function, and if it has a positive leading coefficient, it's going to look like this. Let me start with blue. And again, we have some kind of, depends on the values in the polynomial, so there's kind of like this bumpy part that we don't know what that exactly looks like. What we then do as we can describe this, we can say that it's falling on the left and it's rising on the right. Okay. If I have a negative leading coefficient, it does the opposite. So that would look like this, where it rises on the right, or sorry, rises on the left and it falls on the right. And you'll notice here that they have opposite end behaviors on each side. So when I had an even degree, both sides have the same end behavior. This one has opposite end behaviors on each side. All right, we're going to go ahead and determine the end behavior for each polynomial. We're going to base that just on looking at the degree and the leading coefficient. So what I'm going to do is I'm going to set each of these up to determine what's my degree and what's my leading coefficient. And then from there, we'll determine the end behavior. Okay, so for the first one, our degree, this is a 5th degree polynomial for number 3 because the highest power is a 5. So that means that it is odd. Our leading coefficient is a 1, which is positive. So that is an odd, and positive. So that's going to be this example. So it's going to fall on the left and it's going to rise on the right. Okay. On number 4, here's where this gets a little bit tricky, but I'm going to teach you a little bit of a shortcut. You can figure out the degree of your polynomial without having to multiply it all the way out by looking and summing the degrees of the binomials, or what's in parentheses. So the degree on x minus 5 is a 1, and the degree on x plus 1 is a 3. And so if I add those together, the degree for this polynomial will be a 4. And if you don't believe me, you can test me and check me on it by multiplying x minus 5 times x plus 1 times x plus 1 times x plus 1. When you multiply that all the way out, you're going to get the degree is 4. But if you don't trust me, you can do that multiplying all the way out. Our leading coefficient would just be this value times the coefficient on this one times the coefficient on this one. So -2 times 1 is -2. So we have an even degree and we have a negative leading coefficient. So that's going to look like this. So it's going to fall on both sides. So fall on both left and right. For the next one, our degree is 14, which is even. Our leading coefficient is a 3, which is positive. And so because of that, it's going to kind of look like this. So it's going to rise on both, the left and the right. On number 6, we have r of x equals -2x squared times x minus 1 to the 4th times x plus 3 to the 3rd. Again, we're going to add up all of these degrees to get the total degree of this polynomial. So we have 2 plus 4, which is 6, plus 3, which is 9. So it's going to be odd. Our leading coefficient is -2 times 1 times 1, which is -2. So this is negative. So that would look something like this. So it rises on the left and it falls on the right. So that's how we use the degree and the leading coefficient to determine the end behavior of our polynomials. This is really helpful because if you're asked to draw a sketch of a polynomial, you will need to know what it looks like as the x's approach negative infinity and positive infinity. And so this helps you determine that information. All right, I'm going to stop this video. We're going to have a part 2 where we're going to look at zeros and the multiplicities of zeros. We're going to look at some factoring practice before that, but then we're going to actually graph some polynomials. So please make sure you watch part 2 of this video. Thank you.